So we should speak English. Even all participants here now are Chinese. I feel great honor today to host this conference and for informatics, theoretical computer sciences. And first, let's welcome Professor Wang Bing from Chinese Academy of Sciences. And he will give an important and very interesting talk about long-term forecasting for Tibetan high plain about the climate change. So let's welcome Professor Wang.
Okay. Thanks to Chairman, and good morning, everyone. I'm happy to take this opportunity to talk about the decadal climate prediction or the Tibetan Plateau. My talk have 4 parts, including the background of this study, the ocean observation, the role of the ocean observation in improving Tibetan Plateau climate prediction, and the improvement of TP observations in global climate predictions, and finally the summary and discussion. First, I would like to introduce the background of this study. Here, I want to talk about the reason why we chosen the Tibetan Plateau as a focus of this study. Because the Tibetan Plateau is a very important reason. It significantly influences the regional and global climate, as many scientists have pointed out. Therefore, accurate simulations and predictions of Tibetan Plateau climate is a very important topic in this field. However, there are two difficulties in the Tibetan Plateau climate studies. The first is the scarcity and poor quality of observation data over the Tibetan Plateau region. And the second is the absence of quantitative evidence of the impact of TP on global climate. Therefore, this study has 2 motivations. The first is to improve the data quality and climate prediction skill in the Tibetan Plateau region. And the second is to quantitatively investigate the impact of Tibetan Plateau initial states on global climate at decade schedules. So, for the first motivation, we try to investigate the observations outside Tibetan Plateau on the Tibetan Plateau climate predictions. In this part, we used the ocean observations to improve the decade climate prediction over Tibetan plateau. The estimation of future climate state or climate variations have two methods, including prediction and projection. This classification is based on the source of predictability. As you know, if the internal variability greatly or significantly contributes to the predictability of the events, then the estimate of the future change of this event is a prediction. And generally, a prediction has a relatively short time scale and lead a high quality, more realistic initial condition. Otherwise, if the predictability is mainly come from the external forcing, then this such estimation is a projection. In mathematics, actually, prediction is an initial value problem or initial boundary value problem of partial differential equation. And projection is a pure boundary condition, boundary value problem of partial differential equations. For example, many estimations are prediction problems, such as numerical weight prediction, sub-seasonal to seasonal climate prediction, seasonal to annual climate prediction, and interannual to decadal climate prediction. And the projection problems include the long-term historical simulation and centennial trend simulation and estimation of future climate change. The point here, okay. For example, this is the initial value problem, includes the weather predictions and seasonal to interannual predictions. And here is the projection. And don't rely on the initial conditions. As is a pure forced boundary condition problem here. So for future 100-year time scale, the projection just can give you a long-term trend. And the weather prediction can give the hourly and daily states. And the seasonal prediction can just give a normal prediction over a month or a season. And annual and decade prediction just give the annual mean or monthly mean result for the in the prediction. Here, the decade prediction is a special problem because it relies on the initial states, both the initial states and the boundary condition all influence the prediction. So it's very difficult for decade prediction. Actually, in 10 years now. So in this study, we focus on the decade climate prediction. As you know, the weather forecast is well known by many people. However, very few people know the climate prediction. Actually, climate prediction is also very important in the country because it is the major national need for disaster prevention and reductions and ecology environmental protection. For example, we need to predict the frequent extreme events of heat wave and typhoon and heavy rainfall and so on. On the other hand, we also want to know the decade transition of south waterlogging and north drought in China, so that the government have a good plan for the prevention. The second, the climate prediction is also the major lead of various industrial sectors for medium and long-term planning. For example, annual to decadal predictions of temperature and precipitation can help the agricultural sector plan land use and select crop types. And the prediction of the decadal variation in ocean circulation can help estimate losses from such impacts and prepare for them in advance. Another example is in the energy sector. Annual predictions of temperature, precipitation, wind, and radiation facilitate the planning of thermal plant cooling capacity, as well as renewable energy sources. And the shipping also lead the Arctic temperature predictions, especially the decadal prediction of temperature and precipitation can help healthcare providers improve treatment and mitigation. And the effective predictions of sea level high can help coastal plan their coastlines and in advance. So the climate prediction is very important. Then, how can we make a climate prediction? Actually, climate prediction need to run a climate model, and the running of climate model need a high quality initial conditions and realistic boundary conditions. Here, the climate model is a multi-component climate model, including the atmosphere, ocean, land surface, and sea ice, and so on. And here, the initial condition is very important for the climate prediction because it directly influences the prediction skill. So, how to produce a more realistic initial conditions is very important for the climate prediction. There are two methods to there are two methods for the initialization to produce the initial conditions. The first one is the coupled data simulation, simply CDA, and another one is uncoupled data simulation. Actually, uncoupled data simulation use the standalone component models to separately produce the prior estimation of their own initial condition and then combine the observation. This method uses very advanced or simulation approach. However, this method has its problem. Compared with the CDA, coupled data simulation, the uncoupled method gains less consistency among different components. As for the CDA method, it is still in its infancy, and most of the CDA systems in the world uses very simple and even backward simulation approaches because the coupled model is very complicated compared to any of the single standalone component model. And also the computational cost is very huge. Therefore, generally, the CDA system use a very simple simulation approach. Because the use of simple and backward simulation approach, it is difficult to make accurate decade climate prediction. For example, for important internal variability, the famous Pacific decadal oscillations in Pacific Ocean, very few models can provide an accurate prediction. More than 3 years in advance. Here include many models from world. CMIP. CMIP means the coupled model into comparisons. It is a very important project for the IPCC report. And each report needs the results from CMIP into comparison. And this is the recent, very recent two comparisons in the world. And this model gave the predictions. You can see that this is the confidence level of 95% here. And very few models can give a good prediction and has a significant relationship with the observation here. Just due to the simple and backward simulation method is used in the prediction. Therefore, the scale of predictions 3 years or long in advance are generally low. So from here we can also see the importance of initialization or the quality of initial conditions. In this study, we use an advanced CDA system. This system was independently developed by ourselves using our own DRP 4D1 approach. Actually, this is a 4D1 approach, but can save the time, can greatly save the time computation cost. And we also use the covered model developed by ourselves as the forecast model. And this model is one of the CMIP5 models and shows good performance in CMIP intercomparisons. Here is the model, and this model is developed by my groups. I'm the corresponding author of this paper. And this model uses a coupler to connect 4 components, including the atmospheric model, OC model, and the surface model, and the CS model here. And these 2 models were independently developed by ourselves. And this one used introduced from the American NCAR, National Center for Atmospheric Research in USA. And this one is introduced and improved model, CS model, and this one is also from the same center. And then we add a component. This is the data assimilation component to the coupler here. And then we connect this component to the ocean, atmosphere, and the surface model. So currently, we can separately assimilate the atmospheric observation, ocean observation, and the land-surface observation. And now we have not connected it to the CIS model. So it's called for future study. And the Professor Xu is work on the CIS model. Yeah. Use our covered model and CDA system. We design 2 kinds of experiments. One experiment is the initialization experiment. We conducted 6 2-year CDA cycle simulation to produce initial conditions for decade prediction. And then we use the results from initialization experiments as initial conditions to carry out 36 sets of 10-year handcasts and forecasts. Each set includes 10 members and some members to reduce the uncertainties of initial condition. And we can see that when we use advanced CDA systems developed by ourselves, we can greatly improve the interannual and decade prediction of PDO, the Pacific Decade Oscillation Index. You can see that many models in the CMIP5 and CMIP6 have a poor skill in decade predictions. And our model is here, especially in the decade mean prediction is much higher than other models in the world. Therefore, we can see the the importance of indicial conditions. This is for the global prediction. Actually, the focus of this study is the Tibetan plateau climate prediction. Okay, oops. It is interesting that Tibetan plateau is outside the ocean. Here, we only simulating the ocean observation, and we can find that the ocean observation also can help improve the Tibetan decade prediction of Tibetan plateau climate. Here is the correlation efficiency of 10-year mean summer rainfall in Tibetan plateau. The handcast is the red line here, and the black one is the observation. You can see that the handcast matches the observation very well here, and has a significant correlation efficient with the confidence level of 99% confidence. So it's very good handcast. Just compared to the historical simulation that without any initialization. We also have the same conclusion on the temperature prediction. SAT means surface air temperature. And the handcast is very close to the observation here and have a very high correlation efficient here. And the previous discussion just compare the prediction with the historical simulation. And we also compare our results with the simplified handcasts. Only the handcasts with the same experimental configurations are chosen. And we just got 6 models has the same experimental configuration with our experiment. And we can see that our model here, our prediction is here, and we can see that our model is one of 2 best models to will predict both the precipitation and the temperature in the same time. And the other model, some can will predict the precipitation, but but have a no scale in the temperature here. So, in some time to have a good performance and precipitation and temperature, our model this one, and I think it should be this one. No, this one, yeah. This one there. Yes, this one and this one. So, why the ocean observation can improve the prediction of Tibetan plateau? We here try to provide a possible mechanism. We think the observation data assimilation by CDA can improve the initial states of North Atlantic sea surface temperature here, because the ocean observation can directly improve the initial states of the sea surface temperature here, or the North Atlantic. And then this improvement can also lead the improvement of important variability, AMO. AMO means the analytic multi-decade oscillation index. And this index influences almost the global climate and the regional climate. So this index significantly influence the atmospheric circulations. And some atmospheric circulations can influence the Tibetan Plateau snows, and then influence the Tibetan Plateau summer climate, including the precipitation and surface air temperature here. So this is a possible mechanism. The second motivation of this study is to investigate the impact of the Tibetan Plateau on global climate in perspective of data assimilation and climate prediction. So in this part, we also use the same covered model and the same CDA system, but we only use the observations from Tibetan Plateau to see if the Tibetan Plateau observations can improve the global climate prediction. According to a previous study, here, according to a previous study, the Tibetan Plateau have a significant influence on regional and global climate through three vertical atmospheric circulations, include 2 zonal circulation and 1 meridional circulation. In the east-west directions, 1/3 of the percent of the TP flow forward toward the east in the troposphere, reaches the eastern North Pacific, and then moves downward, which forms a Tibetan Plateau Pacific west-east clockwise vertical circulations here. Here, the Tibetan Plateau is a huge heat source and lead to strong ascent flow. Okay.
Which means Tibetan Plateau
is very high.
very close
I I don't know. Maybe have some influence. Annual in a schedule on the annual schedule, multi-annual, inter-annual schedule, 3 to 5 years. And this influence may be in decadal schedule, 10 years or more, different schedule. But I think a Tibetan Plateau, different scales, yes. But because Tibetan Plateau have a close relationship with the monsoon, why the monsoon also influence the ENSO, El Nino and source oscillation. So Tibetan Plateau also indirectly influence the El Nino and the La Nina. Okay. Thank you for your question. And this is the first circulation zonal. Another zonal oscillation is the another branch, the flow eastward. The first one is eastward, and this one is westward. Here in the upper troposphere and lower stratosphere reaches the Atlantic. This one arrived at the Pacific, and this one reaches at the Atlantic, and then move downward, and then form a Tibetan plateau. Atlantic west-east anti-clockwise vertical circulations. This is a vertical circulation, and this one. And the third one is in Indian Ocean. And this is a meridional circulation. And appear in the tropical, in the troposphere between the Tibetan Plateau and tropical South Indian Ocean here. And also have lead to a strong ascent here, and then move to south, from north to south, and arrived at South Indian Ocean, and then move downward here, and form the Tibetan Plateau, Indian Ocean, north-south circulation here. So three circulation can we can see the Tibetan Plateau influence the global ocean through these three vertical circulations. Based on this impact mechanism of the Tibetan Plateau, the question arises: does the Tibetan Plateau provide a source of predictability for global climate? So, this one of the participation of this study wanted to answer these questions. We used the same advanced coupled data simulation system, a CDA system, to initialize the same global coupled model, F equals G2, but only for simulating the atmospheric observation data or the analysis data only over the Tibetan Plateau area, not a global area. So that we can see the impact of Tibetan Plateau observations on the global climate prediction. We also carried out two kinds of experiments. One is the initialization experiment. We carried out a 59-year CDA cycle from 1958 to 2016. And another experiment is use the result from this experiment as initial conditions to conduct 10-year handcasts once 5 years from 1960 to 2005. We also have three ensemble members to reduce the impact of initial uncertainties. And we also use another set of data to evaluate the handcasts and reanalysis data. The results show that the Tibetan Plateau observation can improve the handcasts of global atmospheric states, include the zonal wind, meridional wind, temperature, job attention height, specific humidity. This is the room square error, the difference between the difference of room square error between handcast and historical simulation. If the value is negative, then means the handcasts have a smaller room square errors. You can see that this is the line for the 0. The red line is for 0. And all the difference is in the left side, means all the negative values, means the handcast has smaller room square error than the historical simulation. This means the Tibetan plateau observation have an important role to reduce the errors in global atmosphere. In particular, the Tibetan plateau observations improves the handcast of global SLP, means sea level pressure, and sea surface temperature. This is the sea level pressure global, and this is the sea surface temperature also global. We only use the data here, a very small region, and you can see that the global everywhere, almost everywhere, can improve the decade prediction. So this is very surprising. That also means the Tibetan plateau is a very sensitive areas in the world. I mean in climate. Also, the Tibetan plateau observations improves the handcast of East Asian summer monsoon. This is the index of the monsoon. Here, this is observation. This is the historical simulations. It has no scale here with a negative correlation coefficient. Actually, the simulation also get a no correlation, maybe due to the limitation or restriction of the observation on the ISC interaction, because the East Asia summer monsoon includes very strong ISC interactions, but this one, because of the simulation of observations can restrict these interactions, so have a no scale. And handcast is a Fourier norm. The Fourier norm only use the initial states from an simulation, and you can see that have a very high scale here. Especially, it is surprised that the Atlantic multi-decade oscillations also improved significantly. The star here means the correlation coefficient passes the confidence level of 95% here. You know, the Atlantic is far away from the Tibetan plateau, but the simulation of Tibetan plateau observations can significantly improve the prediction of this index. You can see that the historical simulation have no scale here, and even the simulation also have no scale. Only the handcasts use the result from the simulation as initial conditions can greatly improve the scale in the handcast. And we also have the similar results from the Indian Ocean dipole index predictions. Here, you can see that also have significant correlations with observation between the handcastle and observation. And the historical simulation have a no scale, and it's very strange that the simulation have a negative correlation, also have no scale, but use its results as initial conditions can lead to a very skillful predictions in handcastle. I don't know why. Maybe need further research. Here we also provide a possible mechanism. How many times? Okay. According to the previous study, the Tibetan plateau in the summer is a future source of heat and lead to a strong ascent here and form 3 vertical circulations. And when we simulating the Tibetan plateau observations use a global coupled simulation, then the singulars of observation can be saved in the Pacific, Indian Ocean, and the Atlantic Ocean. So we have a good initial states in the global oceans. And when we use the result from initialization as the initial conditions, the prediction can be improved because during the prediction, the observation singulars can be released from the ocean for the global climate prediction. This may be a possible mechanism. Finally, I would like to give a shorter summary and discussion. On one hand, the ocean-coupled data simulation can significantly improve skills of predicting Tibetan plateau precipitation and the surface air temperature on decade scales, and also can make the decade prediction of the Tibetan precipitation and the surface air temperature one of the best 2 models compared to CMF5 handcasts. On the other hand, the Tibetan plateau observations can also improve the handcasts of global atmospheric states. Also can improve the handcasts of global sea surface temperature and improve the handcasts of Atlantic multi-decade oscillations and Indian Ocean dipole indexes. However, this improvement is not true in the Pacific Ocean. I don't know why. Here is the prediction of the Pacific Decadal Oscillation Index. You can see that the handcasts have no scale here. So it's really strange. We also carefully investigate the room square error differences of seasonal mean. In before we use the annual mean, and if we look at the season mean surface pressure temperature between the handcast and the historic simulation, we can see that there is a larger errors in the tropical and the subtropical Pacific Ocean. And the Pacific decadal oscillation mainly appear in the winter, and the region is also, some of the region is here. Therefore, these larger Lumen square errors may lead the poor skills in the PDO index prediction. In the future, we have three tasks. The first, we want to simulate the observations from atmosphere, ocean, and land surface in the same time using the CDA system. Currently, we can separately simulate the observations from ocean, atmosphere, and land surface, cannot in the same time. And the second is to upgrade the current CDA system from a weakly covered DA system to an advanced, strong covered DA system. And currently, our CDA system only used to make decade climate prediction. And in the future, we try to extend this system to subseasonal to seasonal climate prediction and even weather forecasts. That's all. Thank you for your attention. Okay.
The first one is I see that you have a picture shows the three circulations about the Tibetan Plateau and the Atlantic, the Indian Ocean, and as well as the Pacific Ocean.
Yes.
And I was wondering, like, will there be another heat circulation containing the Tibetan Plateau and as well as the Arctic Ocean?
Very good questions. Currently, we did not find such a circulation to connect the Tibetan Plateau to Arctic oceans. I think it may indirectly influence the Arctic oceans, I think. But I didn't find the direct impact here. I don't know, maybe Professor Shi can answer this question.
Okay, and another small question, because I'm still a high school student and maybe my...
High school students?
Yes, high school student. 八中的.
Okay.
And my knowledge about computer... No. My knowledge about computer science is like very little, but I was... after listening your lecture, I feel like the CDA model and the CMIP 5 or 6 are models that solving the problem by seeing it as a prediction, which is mainly connected with the initial value. Is that right?
Yes.
And however, you've mentioned in the very beginning that the decadal predictions is at the transitional state of predictions and projections. So I was wondering, like, if we can solve the problem by seeing it as a force boundary.
Boundary and the value.
Yes, the force boundary one. So by using the Lagrange, 就是拉格朗日乘子法，或者就是我去用 Lagrange multiplier or the penalty function to solve it.
Okay.
I don't know about the mathematics. But however, here, actually, in our decade climate prediction, the boundary value has a longer time schedule, more than 10 years or more or longer. While the initial condition just impacted a short time scales, say 10 years or less, 10 years or less. But I don't know if we can use the Lagrange method to solve this problem.
It's a good idea.
Very good. Thank you.
Do you have any other questions? Or maybe some comments? Would you like to say something?
Yeah, I do have a question about the future climate change of the Tibetan Plateau. So, what's the, for example, will it be have a bigger role, for example?
Maybe for next 10 years.
For me, 10 years.
Next 10 or 20 years, maybe in there.
Role for predicting global climate change, especially great volatile.
Actually, here we didn't show the prediction, just give the result of handcast. In the prediction, I think the snow and the ice will be greatly reduced in the future. But in 10 years, maybe also can be reduced to some extent, but not great largely, I think. Yeah.
Thank you, Professor Wang. And I'm very interested in two questions. The first question is, we know that there are interactions between different scales, and you do the simulation of the decadal scale. Are there any affections from other scales? For example, the yearly or the longer term scales.
You mean the annual or centennial?
Yeah.
Yes, I think have this impact. Actually, the decade scale is the background of annual and seasonal scale predictions. Why is important participation to the centennial trend, I think.
Okay. And the second question is, are there any standard benchmark for the decadal prediction?
So benchmark, I don't know which model is benchmark, but in the world I have many climate model, climate system model, and all system models, and different model maybe have different results. So we have the uncertainties between the model predictions and the simulations.
Yeah. So are there any standard data or standard index that we know whether it is predicted better? For example, where we have you use IMSE, but in fact there are extreme events or raining events or the tipping change states.
Yeah.
So I think to build such kind of standard benchmark maybe is important for this problem.
Yes, you're right.
Yeah.
I think it's very difficult for the current model to capture the tipping point. I think it's very difficult. Maybe can combine the AI technique or other methods to catch the tipping point, I think. For the extreme events, is very difficult for a climate model. Yes.
Okay. And my third question is about what's your opinion to compare the current climate model and the recent AI technologies?
Yes. Actually, the AI-based model currently use the results from the dynamic model. If they have this data from the model, they cannot estimate the AI-based model, I think. So I don't believe the AI model can replace the dynamic model. But AI technique is a very good technique to help the model to improve the skills, I think.
Thank you.
Especially to save the time, to speed the prediction, I think.
Thank you.
Good talk and good discussion. Thank you so much for
thank you.
Thank you so much.
Thank you.
15 minutes for tea break.